Yes, class, am I audible?
Yes, ma'am.
Yes, ma'am.
Alright. So Ahmed, Anushka, Imad, and Jeeva. So till now only 4 students have joined. Okay, let's start with the class. I have waited for more than 5 minutes, I think. But yeah, so join there. Alright, so in the last class we had started with LCR circuits. Series LCR circuits we did, where we had seen it was a combination of a circuit having a resistor connected in series along with a circuit having an inductor along with a capacitor. And all the individual properties that we had seen for all these individual circuits, like purely resistive circuit, purely inductive circuit, purely capacitive circuit, so that formed our LCR. For this, we had the phasor diagram as well. For this, we had the impedance as well. So some things were fixed, some things were unknown. Like if it is XC greater than XL, or if it is mentioned to us that XL is greater than XC, depending upon that, we had the phasor diagram, whereas which was fixed, resistor 1 was continuously fixed with us. Then apart from this, we had seen the net resistance value, which is referred to as the impedance. So impedance was Z is equal to under root R square plus XL minus XC whole square. It could be XC minus XL whole square if your VC is greater than VL. All these phenomena were there. And then we had seen a question. Okay, this was a question that I had left because see, one topic is involved over here that we'll start, which is known as the resonance condition of LCR circuit. Series LCR circuit you have, so that is the resonance condition of the series LCR circuit that we'll start with. Now, see in the resonance condition, among the LCR circuits, now LCR circuits among AC is itself a very important topic. But within this LCR circuit, you have resonance as a very, very important topic. Resonance condition of LCR circuit simply means your impedance value is very less. Now, how can the impedance value be less? See, if I say XL and XC both are equal, somehow I'm saying XL and XC both are equal. So if both are equal, let me see what is the value of impedance that I'm obtaining. If both of these are equal, so Z will be equal to R square plus XL minus, instead of XC, I can write it as XL only because both are equal right now, under root square. Both are cancelled, under root R square, which is equal to R. It means Z is equal to R. Now see, here you were getting a bigger formula. Something got added to something. You got a bigger formula comparatively. Now what is happening? See, now your current is IRMS is equal to VRMS divided by Z, or any of these values. Or you can even take I naught is equal to E naught divided by Z, any of these values. Now Z is equal to R. It means initially the value of Z was a longer value. Now we are just having it as equal to the resistance. No component of XL or XC are getting added or subtracted. So it means Z has decreased, right? Z from both of these cases has decreased a lot. If your Z decreases, it means your current resistance is decreasing. Resistance will decrease. Definitely current will increase because there will be no obstruction in the path of the current. When the current will be flowing through the wires, there won't be any obstruction in it. So here also what will happen, since Z is becoming less, current will increase. And this increment in the current, when the maximum current is present, this condition we call it as the resonance condition. When the current is maximum, impedance is minimum, Z is equal to R, and one more thing, XL is equal to XC. But main statement of resonance is what? Main statement of resonance is this: a series LCR circuit is said to be in resonance when current through it, whatever is the current through it that has passed through this, has its maximum value. So current has the maximum value. It means impedance has the minimum value. And for impedance to be minimum, XL should be equal to XC. This is a condition. So if resonance condition theory part comes in the numerical, you can directly use it. If in the theory part it comes to prove the resonance condition of LCR circuit or to show whatever is the meaning of resonance condition of LCR circuit. So what you're going to do, XL is equal to XC. This you'll write later on. Firstly, you have to mention this statement. A series LCR circuit is said to be in resonance when current through it has its maximum value. Then you will show this, and you will show that yes, Z is having the minimum value, that is Z is equal to R. This you will show, and then you can prove it that yes, definitely current is greater. And this depends upon the marks. If it's just for one marker, then you can write this statement only. If it's for a two marker also, do mention XL is equal to XC. Now see, if XL is equal to XC, one more thing before you can note it down. XL is equal to XC. But what was the formula of XL? Someone new is here. Joe Edelbert Johnson.
Yes, ma'am.
This is your first class, no?
Yes, ma'am.
All right. So how much syllabus has been done in your school, Joe?
We're doing the nucleus chapter now.
Okay. Modern physics here. All right. Yes, others. So XL's formula we had done in the last class, inductive reactance. What was the formula of inductive reactance?
2 pi nu L.
2 pi nu L. Perfect. 2 pi nu L, or so you can say, let's write it as omega L only. Good. And XC? Formula of XC.
By omega C.
Yes, Ahmed?
1 by omega C.
1 by omega C. Definitely correct. So only Ahmed has revised the last class. Correct. This is right. Now see, from here, if I write the value, if I multiply omega here and I put L back here, this becomes omega into omega and 1 by LC. Right. I have just exchanged this inductance value with the frequency, angular frequency. So this becomes omega square is equal to 1 by LC. Omega becomes what? Omega becomes equal to 1 by under root LC. But this is what? Omega we have been studying that this is the angular frequency. If your linear frequency is required, what will you do? See, we had seen a relation, omega is equal to 2 pi nu. This is a relation between the angular frequency and the linear frequency. So linear frequency can be written as omega divided by 2 pi. So what is omega? Omega is 1 by under root LC divided by 2 pi. So linear frequency that you're obtaining is 1 by under root LC into 2 pi. This frequency is known as the resonant frequency. Resonant frequency also, in the exam, you can get one more term in your board examination. Natural frequency. So if these two terms are mentioned in front of the frequency, then do get an idea that this is referring to this condition, that is your resonance condition. So the question completely becomes a case of resonance condition. And you have to identify this in your answers, that whether XL is equal to XC or not. Check the magnitude. Units will be the same. You just check the magnitude. For example, in the question which I had left in the last class, here a circuit was given and XC was equal to 4 ohm, XL was equal to 4 ohm. So XC and XL were equal. This gave the resonance condition. Likewise. All right, class. So this is a small topic, but questions from resonant frequency, especially this derivation, this comes as a 3 marker or 2 marker in the exams to prove. Otherwise, a full resonant question can come in theory, or simply numericals can come from this. All right, note it down till here. Any doubts you have, let me know.
Am I?
Yes, yes, Ahmad. Say.
Yes, sir. Can you just explain this? Independence is minimum. So, what is Z decreasing here? Just can
C. Yes, yes, I'll show you. Z is the impedance. Impedance is the resistance. Whatever you have studied for resistance, I is equal to V divided by R. In general, using Ohm's law, we have this I is equal to V divided by R. So here for a series LCR circuit, instead of this R, we had this Z, right?
Yeah.
Earlier, this was the whole statement. Z is equal
Okay.
to under root R square plus XL minus XC whole square. So it was something more, a greater number. Right now, what is happening? This whole term has reduced to 0. This term is 0. So Z's value is only R. It
Okay.
supposedly here it was, let's say, 30 ohms on solving. Now the resistance value must be only 40 or some less than value. Let's say this was 30 ohms. So it would be lesser than 30 ohms. You're getting a lesser value of R. Only R part is there. This part which was getting added up, this is not present. Right?
Okay.
So that's
Yes.
why we're saying Z is now less. And if Z decreases, current will increase. All right.
Okay. Okay.
Ma'am,
Yes, Anushka. Yes, Anushka.
ma'am, today's class is going to be for 2 hours, right?
Yes, yes, 2 hours. Now your duration has been increased to 2 hours. Fine.
Yes, ma'am.
Though your syllabus is now stable, you're not lagging behind. See, AC will get completed this weekend only, and we'll start with EM waves only. By tomorrow, we'll start with. And EM waves is a chapter of only a single class. After that, we'll directly start with ray optics. But still, if we do not increase the time duration, no, we'll get a very small time for revision. As you see, so many students are getting added up, and so much revision of chapters is left. All right. See, a question is there that says that a resistor of 12 ohm, a capacitor of reactance 14 ohm, and a pure inductor of inductance 0.1 Henry are joined in series and are placed across a 200 volt 50 hertz AC supply. You have to calculate the current in the circuit and the phase angle between the current and the voltage. So this is based upon normal series LCR circuit. All these three, see, R is here, C is over here, and L is here. So LCR circuit connected in series. So simple question on series LCR circuit. Firstly, we'll have to find what? We'll have to find the impedance, Z, because voltage is given, ERMS is given to you. How will we find out the current? Now see, R is given to you as 12 ohm. Capacitive reactance is given to you as 14 ohm. But what about inductive reactance? Inductive reactance is not given. This is inductance that is given. Inductive reactance is a resistance of the purely inductive circuit. So its SI unit should have been ohm. Since it is given Henry, it means this is the SI unit of self-inductance or mutual inductance. So definitely we are referring to a single resistor only, single coil only. So this is self-inductance, which is given to us as 0.1 Henry. So let's find out XL. So as that time only, a few minutes back, Ahmed has answered that XL's formula is omega L. See, omega is also not given, linear frequency is given, 50 hertz. All this is the information that is present. All these are the information that are available to us. So XL can be written as omega, we can write it as 2 pi nu, and L is present here. So see XL, what we'll obtain. 2 into pi, it is already mentioned as pi, take pi's value as 3. So 2 into 3 into linear frequency is 50 into 0.1. This much you will obtain. Fine. So XL's value, see from pi, see, pi value is given in the question. This is, that's I'm not taking it as 3.14 or 22 by 7. This mention is given specifically for this question. All right. Okay. So we are left with what? So this becomes what? 50 into 6, 3. 0, 300 into 0.1, 30. So, all right, XL will come out to be 30 ohms. So now XC, we have 14 ohms, XL, we have 13 ohms. Which is greater, XL or XC? Which one is exceeding?
XL.
XL, definitely, yes. So Z becomes under root R square plus XL minus XC we'll write whole square. Why won't we write XC minus XC square? Because XL has a greater value. And if XL is more than XC, because we want to find out resistance value, and resistance cannot be negative. So that's why instead of taking the modulus, we are subtracting the higher term by the lower term. So what do we have? 30 minus 14, this becomes 16. So Z will be 12 square plus 30 minus 14 whole square, which becomes 12 square plus 16 whole square. So Z is, this is 144 plus 16 whole square is 256. 256 under root. So this becomes, Z becomes equal to under root 400. And under root 400 is what? 20. So you get 20 ohm. So 20 ohm is the what? 20 ohm is the net resistance of the circuit that you're obtaining. All right. Otherwise, our impedance, this, otherwise, the resistance of the purely resistive circuit was 12 ohm, XC 14 ohm, XL 30 ohm, right? Now, the net resistance of the circuit, what we are obtaining. Otherwise, this purely resistive circuit, purely inductive circuit, purely capacitive circuit all have combined together. Now, the resultant circuit that we are obtaining, this is the impedance. So, impedance is the right now the net resistance of this whole complete circuit that we are obtaining. So, instead of writing 12 ohms, instead of writing 14 ohms, instead of writing 30 ohms, we'll be directly writing with 20 ohms that we are getting. So this becomes the final answer for us. Now coming to the second part of this. Phase angle between current and voltage. So phase angle between current and voltage you can obtain. This is the answer for the first part. This is the answer for the second part. Now see, you can even use XL minus XC. That will be perfect for this question because you have value of all these three quantities. So we had seen two formula for this also. Tan phi is either XL minus XC by R or XC minus XL by R. This is XL minus XC by R we'll use because XL is greater. So this again becomes 30 minus 14 by R is 12, 16 by 12. So we get 4 by 3. So phi becomes equal to tan inverse 4 by 3. This is the answer. All right, note down this question, note down the solution. Wherever you get stuck, let me know. I'll repeat it.
Ma'am,
Yes, Jiva.
could you repeat the second one? I was not able to understand.
Yes, yes. See. This we had done, remember, using impedance triangle, tan phi and cos phi. So here cos phi is not necessary because R and Z both are equal. What we can do, since we have XL, XC and R with us, either we can use this equation or we can use the second equation. Now, whether to use first and second, this is determined by what? This is determined by whether XL is greater than XC or XC is greater than XL. So here we have XL greater than XC. So we'll put XL minus XC divided by R. Using this impedance triangle only, we have obtained this tan phi. Fine. Now, then we put the value of XL as 30, XC as 14, R as 12. 16 by 12 is obtained, which can be written as 4 by 3. So tan phi came 4 by 3. Phi will become what? Tan inverse 4 by 3. Got it, Jiva?
Yes, ma'am.
All right. Yes, the class written till here. One more topic is there, which is a part of resonance only, Q factor. Last part of LCR circuit. Then we'll move on to one or two circuits are left. Very small circuits are there. LR circuits, RC circuits, that we do. That won't take so much of time. Mainly Q factor is left. Let's discuss with that. If anybody is writing the above part, let me know. I'll scroll up back. Now see Q factor. Q stands for what? Q is basically quality. This is the quality factor. This Q factor that we are referring is quality factor. So you get a question in your exam. What do you mean by sharpness of resonance in a series resonance circuit? Or find the expression for this Q factor. These two parts only come. So we'll be discussing that only. But before that, let me plot a graph first. Then you can understand it. I have drawn a graph. I'm plotting it between the current I naught and the angular frequency omega. I naught is here, angular frequency omega is here. Now see, I am taking the variation of the current's amplitude. For example, if I take a part of a graph variation like this over here at this point. See, at this point, what will happen if I have taken a part of the graph or any variation at this point? See, here it means current's value is very low. Till here, the current must be having its maximum value even. So if such is the case, it means the resistance over this region will be very high, high resistance over here. If I take a region up here, this will be having moderate value of resistance because moderately the current is high. So moderate R. If I take up a very high maximum value of current, very high. See, this is so much high, highest value among all of these. So according to the relation V is equal to IR, since I and R both are inversely proportional to each other. So here you will get the lowest value of the resistance, low value of current will be obtained. Fine. So this figure is basically, it is showing you the variation of current amplitude I naught in a series LCR circuit with angular frequency omega naught. Take it as omega naught. Or let's say now this value is what? This value, this is the highest current, highest value of current that is present, maximum current. What is the condition known as when the current is maximum? Resonance. That's only what we have studied till now. So let's say this is the resonant frequency, omega R. Let me write it down. So at this point, you will get a value of the angular frequency for 3 different values of R. Can you see low value of resistance, moderate value of resistance, high value of resistance? And omega R, we all know, omega R is simply 1 by under root LC, the same omega R, resonant frequency. So the resonant frequency is independent of R. This resonant frequency is independent of R. Whatever is the value of R, low, high, moderate, you can notice that this line is still lying in the middle. This is depending upon the values of current. So this is what? This is independent of the value of resistance. But the sharpness or the peak of this current graph or the peak of the graph, this is dependent on R. Can you notice this fact? This is a little blunt graph. This is a very sharp graph. So the sharpness of the peak, how much the sharp is peak, the peak will be sharp. This depends on the value of R. If the R is low, the peak will be very sharp so as to get a maximum value of current. Likewise, now the peak is higher for small values of R. Low R, higher. Blunt peak, high value of R. Like this. So this sharpness of a resonance, how much sharp a resonance, this much, how much sharpness of resonance is there? Sharpness in the peak of the graph, you can say. This is measured by a coefficient which you call as the Q factor or the quality factor. How much sharp is it? That the calculation or the measurement, you can say by measuring the measurement of this, how much the maximum value of current is there. So you'll not be requiring these circuits. these graphs. Now see what is the definition of Q factor. Definition of Q factor is important because you cannot write the definition of the Q factor like this. No, it just measures the peak value of current. This is just for our knowledge. This is just for our understanding that yes, it measures how much peakness is there in the graph. Whether the graph is a flat one, graph has a narrower tip like this. So now see the definition is what? For understanding definition, no, the actual definition that you'll be writing in your exam. Let me plot the graph once again. Now I'll be taking that graph was just for your understanding. Now, since we all know right now that the resonance will be obtained at the maximum value of this graph only. So I'll be taking the maximum peak value of it. Now see certain terms that are required within this. This is what this we have studied in the above graph. See, that above graph was just for understanding the low value of resistance higher. That is not required. If Q factor comes, this is the definition. This is the graph that you'll plot, and the derivation. If the derivation is asked, then the derivation for the formula of Q factor. The rest of the things, nothing is required. So this is the graph. This is the resonant frequency. Let's say at one point. This is one point of the graph. And this is one more point of the graph. This is what? This is for the frequency. Let's say this is some value omega 1. This is omega 2. 2 points I have chosen on the either sides of the resonant frequency. Now see, Q factor is actually what? Q factor, it is the ratio of two quantities. What is the first quantity? What is the second quantity? Now the first quantity is basically the difference of the frequencies that are taken on either sides. Either sides of what? Either sides of the resonant frequency. So omega 2 and omega 1's difference will be taken. That is omega 2 minus omega 1. Difference of the frequencies that are taken on the either sides of the resonant or main frequency. Fine. Now 2 what? Divided by what? Divided by the, this is actually resonance frequency. I have written it up. Ratio of resonant frequency to the difference in the frequencies. No, so resonant frequency will be here. Now here, as I've told you, this is omega 2 minus omega 1. Now one more thing, class. If you are having the value of current amplitude I naught as E naught by R, let's say. So at this point, no, when you are taking, let's say this point, where the difference of frequencies are taken, your current becomes 1 by root 2 times whatever is at the normal value. Whatever is value is at the resonance. Let's say I naught is equal to E naught by R is there. So current amplitude will become 1 by root 2 times the resonance value. It means E naught by R will be here. It will become 1 by root 2 times. I was what? At resonance. I naught was equal to E naught divided by R. At this frequency that I am choosing, the resonant frequency, now at these each frequencies, the current's amplitude values become E naught by R is there at resonant. It becomes 1 by root 2 times. These are those two frequencies that are taken. These are not some random frequencies that are just plotted on the graph. These are such points in the graph which are giving you 1 by root 2 times. And also, class, this gap now that you're obtaining, this omega 2 minus omega 1, this is known as the bandwidth. So you can say Q factor is what? It is the resonant frequency. This is the resonant frequency divided by, instead of writing difference of the frequencies, you can easily use the term bandwidth. Bandwidth. Now coming to the definition, what I have written up. See, quality factor is what? So Q factor or quality factor of a series resonance circuit, means series LCR circuit, is defined as the ratio of resonant frequency. In the numerator, you have resonant frequency to the difference in the two frequencies taken on both sides of resonant frequency. To the difference of resonant frequencies taken on both the sides of resonant frequency, such that at each frequency, means at each of these values, at each of these, current amplitude becomes 1 by root 2 times the value at resonant frequency. Here, this is the definition what is written. So before we do the derivation of this, no, this has a longer derivation. Just copy this down. This has a very long derivation. It's unlike the natural or resonant frequencies. Note it down till here. The definition, these two graphs, then I'll do the derivation.
Ma'am, can you scroll up? Mm, 2 minutes. Yes, ma'am, you can scroll up.
All right, now let's come to the derivation. See, derivation is a little lengthy of this part. So wherever you're not able to understand, stop me in between only. All right, derivation, I'm again telling you, lengthy. So yes, chances are there, the derivation can be asked, but mostly from resonance. No, derivation of natural or resonant frequency is asked. So that is most important. First revise that, then after that revise this part. Now see, usually we have seen what current's value is root 2 r, E naught divided by root 2 r. So at resonance, Z is equal to r. At this condition, r is root 2 times the value of resonance. So Z will become, instead of r, we'll be adding this additional component root 2r. Right. And now what is the formula of the Z? Z's formula is r square plus XL minus XC whole square is there. Instead of XL, I'm writing this complete term. XL minus XC whole square under root is equal to root 2 divided by r. Root 2 multiplied by r. Because this is the value of z, formula of z, and this is the value of z here, root 2r. Now, just let's take the square of all the terms on the side. So this becomes r square plus omega L minus 1 by omega c whole square. See, root 2 here gets cancelled, root gets cancelled, and this also becomes square. We'll be left with this. Now, value of r square, this becomes 2r square minus r square. If I shift this r square, that becomes omega L minus 1 by omega c whole square is equal to r square. From here, if I take the root on both the sides, what do I get? See, from here, these two important equations will be formed. If you take the root, omega L minus 1 by omega c is equal to plus minus r. So one you have omega L by 1 by omega c as plus r. Other one you will have 1 by omega L minus 1 by omega c minus r. Now two frequencies were there. So let me take this as 1, 1. Take this as 2, second frequency. We are considering both the frequencies, no, which are present on either sides of the graph. So this I have taken at omega 2, 1. This is omega 1. So these are two equations, equation 1, equation 2. Now these two equations will be necessary. First, tell me, is it clear till this step?
Yes, ma'am.
Yes, ma'am.
Explain
Clear.
this part again.
Yes, I'll explain this part. See, firstly, Z's formula is r square plus xl minus xc whole square under root. And also here at this condition, Q factor, Z's value is root 2r, not r. What we have read right now, this becomes root 2 times r. So this is equal to root 2r as well. Now, if I take the square on both the sides, I'm left with r square plus xl minus xc whole square is equal to 2r square, right? xl minus xc whole square is equal to 2r square minus r square, which gives r square. This is what is till this step. Now, instead of xl minus xc, I'm writing omega L minus 1 by omega c, because xl value we all know is omega L and xc's value is 1 by omega c. So this term is equal to root 2r. Square got cancelled. This r came. So 2r square minus r square gave this r square. Now I have taken the roots. Plus minus 2 roots you get, a positive root and a negative root. So one of the roots I have considered it at random. It has 1, omega 1, and other one as omega 2. Why omega 1 and omega 2 only? Omega 1 and omega 2 are these only. This omega 1 and omega 2. This is what we are getting. All right. Now is it clear till here? Clear to all of you? Okay. Now see, if you have these two equations, using these two equations only you will get your final answer. So please, whenever you're revising this derivation, please revise and practice this in 4 steps only. So this becomes your first step. Till here, your aim is to obtain these two equations. All right. This is the first part of the derivation. Now add both these two equations. Add 1 and 2. Both these equations are present, add both of these. So this becomes what? What equations do you have? You have omega 1L minus 1 by omega 1C. Let's add the right hand terms together and left hand sides terms together. So omega 1L minus 1 by omega C plus omega 2L minus 1 by omega 2C. And what do you obtain on the other side? You get plus R minus R. This is what we have obtained. Now from here, let's take omega 1L and omega 2L. Let's take L common. So we'll get omega 1 plus omega 2. L has been taken common from these two terms. Carefully listen, class. Now these two terms are left. From here I am taking 1 by C common, minus 1 by C. So now what I will be left with again? I will be left with 1 by omega 1 plus 1 by omega 2. Got it? Minus 1 by omega c, minus 1 by omega c. I am left with this term, and plus r minus r gives 0. Now, let me simplify these terms. Omega 1 plus omega 2 into L minus 1 by c. Let me take the LCM over here. So this becomes omega 2 plus omega 1 divided by omega 1 into omega 2. All right. These two terms I have obtained now. Now value of omega 1 into omega 2. Let's put this entire term over this side to make it as positive. L, this is equal to this whole term, 1 by c omega 2 plus omega 1 by omega 1 into omega 2. So omega 1 plus omega 2, omega 1 plus omega 2 gets cancelled from here. So value of omega 1 into omega 2 from this comes out to be 1 by LC. This is an equation that will be obtained. Let's say equation number 3. Tell me, till equation number 3 is clear? This is the second part when you add it. Clear or not till this part? Third, this is the second part.
Yes,
Yeah?
ma'am. Yeah.
Okay. So when you'll revise it, no, do it like this only. First, make your aim to revise it till here. Once this is done, then add these two equations and practice. See whether you're obtaining omega 1 into omega 2 or not. Now coming to the third part of the derivation, we'll subtract both the two equations. Subtract 1 and 2, both the two equations. So see, instead of wherever you had plus, now you'll be having minus. I'm not writing it again because obviously same steps will be repeated. If you add both, if you subtract both these equations, omega 2 is equation from omega 1 equation, what will happen? Everything here will be the same except for the signs. Signs will just get reversed. So what will happen? Omega 1 minus omega 2 will be here instead of plus sign that was present. And minus 1 by c was there above. This becomes plus 1 by c. And here we had omega 2 plus omega 1 by omega 1 into omega 2, remember? So this becomes minus. Now this won't be 0. Why? Because that time it was addition. So plus r minus r gave 0. This time it is what? This time this whole term, this is r minus r. Other term was negative, no? Here minus r was there. This is the subtraction sign obtained. So this gives r plus r is equal to 2r. Did you understand? See, one term is plus r, other term is minus r. So if you add these two terms, plus r plus minus r, you have added these terms. So you get r minus r, which is 0, the way we had obtained this in the above part. Now what is happening? Plus r minus r. This was addition, this is subtraction. So this becomes r minus r, that gives r plus r, which is 2r. So now when you add it, you will get 2r. Clear why this is 2r? This won't be negative now. Both are getting subtracted. So in subtraction, one negative will lead you towards the positive. In the above part, it was addition. So directly we could write plus r minus r as 0. Now this part is there. So to solve this part further, what we can do, we can take the, first we can do one thing. Let's take omega 2 minus omega 1 common from both of these. Because if we take omega 2 minus omega 1 common, a little simplified part will be available. Let's take omega 2 minus omega 1 as common. So if I take omega 2 minus omega 1 common from this part, I'll be left with only L. And if I take this part common, I'll be left with 1 by c omega 1 into omega 2. This is equal to 2r. Now is the use of the third equation that we have obtained, omega 1 into omega c. To obtain that only, so much derivation and so much calculations were done. Equations were added, omega 1 into omega 2, to obtain this 1 by LC. All right. So omega 2 minus omega 1, L plus 1 by c. Instead of omega 1, see, omega 1 into omega 2 is 1 by LC. So 1 by omega 1 into omega 2 will be LC only. So this part becomes LC. 1 by omega 1 C. 1 by omega 1 into 1 by omega 2. This part can be written as LC only because omega 1 into omega 2 gives 1 by LC. So this part is LC. This much is left is equal to 2R. CC gets cancelled. Omega 2 minus omega 1 into this becomes L plus L is 2L into 2R. From here 2 also gets cancelled. And omega 2 minus omega 1 is R by L. This is obtained R by L, and this is the fourth equation. Tell me, till here is it clear? This fourth equation, how this is obtained?
No, ma'am.
Yes,
Can you just
ma'am.
explain that again?
Yes, somebody was having doubt. Imad, yes, Imad,
Yes,
say.
Yeah, that fourth equation, can you just explain that again? Because
Yes.
half of it I understood, but this one.
Okay, till which step? This part you have understood?
Yes, ma'am. That is okay.
Okay. See, did you understand this part? Why LC was kept here?
No.
Okay, I'll add. Look over here. This equation, this is written what? 1 by C omega 1 into omega 2. Just focus on this part because if you'll understand this, no other parts are very, very simple, easy mathematics.
Okay.
See, omega 1 multiplied by omega 2 was 1 by LC, right? We had derived it using addition part, right? Yes. Now see, here we have, if you separate this term, this can be written as 1 by C and 1 by omega into 1 by 2, right? This whole term.
Okay.
Okay, this is the same thing. I'm just separating it. So if omega 1 into omega 2 is 1 by LC. So 1 by omega 1 into 1 by, omega 2 means just reciprocal of it will give you LC by 1. This term will also get reciprocated, right? If you reciprocate this term. Yes, so 1 by omega 2. Yes, we have just reciprocated because we want 1 by omega 2 into, or even if you put the value of omega 1 into omega 2 here, that is 1 by LC, 1 will come here, LC will go into the numerator. So directly you will get LC. So this will be LC by C. Clear this part?
Yes.
So CC gets cancelled. Here you get 2L, L plus L. So all these are getting multiplied. So 2 here gets divided and you get omega 2 minus omega 1 as R by L. Clear to all now? Clear to your math?
Now clear.
Okay. So now see, omega 2 minus omega 1 is equal to R by L. This was an important part to get, and for that only we had done so much of derivation. Now coming back to the Q factor. See, one more formula of Q factor. Now Q factor is what? Omega resonant, that is the frequency at resonance. Subtraction of both omega 1 minus omega 2. Directly here, omega 2 minus 1, omega 1 also you can write what we had written over here. All right, and this term, one more formula for this now becomes what? Omega R is there. Instead of omega 2 minus omega 1, what we have obtained now? R by L. So this becomes one more formula for this. Q is equal to omega R L into divided by capital R. This is one very important equation of this, what we have obtained. You can name this as equation 5 because so many equations are there. So if you name the equations, you can remember it easily. One formula is this. To obtain this, we had done so much of the derivations. Now see class, one more formula. Not only this, this is also one important formula, but one more formula we have it from this. See, Q is omega at resonance is equal to 1 by under root LC. Natural or resonant frequency, not natural or resonant frequency, angular resonant frequency. We have resonant frequency is 1 by under root LC, right? So if I can write it as omega square is equal to 1 by LC. If I square this term, resonant term, it means I can write this as omega R into omega R is equal to 1 by LC. Same thing, just reversing the derivation for what to obtain this. We had done it in the other step. First we wrote this, then we wrote this, then we obtained this. Now I had reversed it till this step. Let's exchange this. Take 1 omega R over here and put 1 L over here. Let's exchange this with this 1 omega R and L. Let's exchange these terms. So what do I obtain? Omega R here. I obtain this L comes here. This becomes 1 by omega R, and here this is capital C. Omega R into L. Can you see omega R into L was here also? Right now that we have obtained omega R into L. So omega R into L is what? Quality factor into resistance. Q into R. This is what is omega RL. So this is quality factor into resistance is 1 by omega R into C, or quality factor can be written as 1 by omega R capital R into C, or if you write the value of omega R as 1 by under root LC, you get Q value as 1 by R under root L by C. So this is one more formula that is required. Maximum chances are there that directly questions from this Q factor will be asked in numerical form. But you have no idea, you can get an equation also to derive this, find the expression as a full-fledged 5 marker. So be prepared with this, though chances are less. Coming of Q factor in your exam for derivation are very less. It's a very lengthy one. Usually this is not given. Clear? So this is the formula that you'll use, equation 5 and equation 6, especially equation 6. Equation 6 is important from your numerical point of view. All right, now you can copy it down. And whenever you're revising, revise it into 4 parts only. First, obtain this part when these 2 equations are there, then add these. Second part done. Subtract these. Obtain omega 2 minus omega 1. And once you've obtained omega 2 minus omega 1, then to this final step of the calculation. All right, note it down. These margins part were just for your understanding. If you want to skip it, don't write this part. Write down the sphere part only.
Ma'am,
Yes, yes, Asta, say.
how did the last formula come? Q is equal to 1 by R root of L by C.
This is how, if you keep omega r is 1 by under root LC. So if you keep here 1 by under root LC, what will happen? Root over LC will come here. See, it will be like Q is equal to root LC by RC. Fine. So if, how can you write 1 by, this is LC by C only. So I have just taken common under root C into under root C, just to rationalize it. So you get under root LC together. 1 by R is already there. So just putting the value under root LC for this equation. All right, this into omega R.
Yes, ma'am.
Okay, let's do a numerical on this, based on this. See, this says in a series LCR circuit, resonant frequency is 800 Hertz. So omega R is 800 Hertz. Half power points are obtained at frequency 745 Hertz and 855 Hertz. So frequency second is 855. Frequency first is 745. Q factor and bandwidth. Q factor is omega R by omega 2 minus omega 1. 800 by 855 minus 745. This gives us how much? 0, 1, 1, 110. So if you solve it, 11 into, see 11, if you multiply it by 7, you get 77. So around this, you will obtain 7 point something, 27, like this. Just check the calculation once again. And bandwidth is what? See, bandwidth is this part only. That is omega 2 minus omega 1. It means 855 minus 745 only. That is 110. This much. All right, note down this question.
Ma'am, could you show the question?
Yes, I'm showing. Somebody wants to write down this part. I'll show it. All those who have completed, just text me done in the chat column. Sarazandan. Job, did you understand today's class? Job Adelbert Johnson.
Yes, ma'am.
All right. So you can take the backup lectures also from me because, and most probably this chapter will end by tomorrow. So after this, tomorrow's class, see, most probably we'll be starting with ray optics in the next week. EM waves and ray optics we'll start in the next week only. So the whole first book will be over. So what